Yeah.
Alright, good start anyway. So, remember the Friedman equation. Friedman equation says that a dot squared over a squared is a pi to the 3c squared epsilon minus kappa c squared over r squared a squared. And we have the fluid equation as well, which says epsilon dot plus 3 a dot over a, epsilon plus p equals 0. In the equation of state, it says that p equals w epsilon. So we looked at various different possibilities here. We primarily focused on the idea that epsilon is the sum over different pieces with different energy densities, and these pieces can have different equation of state parameters. So the energy density is the total energy density, the energy density of matter, plus the energy density of radiation, plus the energy density of multiple constants, plus whatever other stuff may or may not exist. And similar to the pressure is the sum over the individual pressures. And this makes sense. So suppose we've got a gas with molecules in the room, pressure of the total gas is the same as the pressure of nitrogen plus pressure of the oxygen plus pressure of whatever. So this equation and this equation are basically the states of conservation of energy, and they make perfect sense. If we have a single component universe with only one thing in it, we found that the energy density as a function of the scale parameter is the energy density today times a to the minus 3 times 1 plus w. And we notice that w is 1/3 for radiation, 0 for matter, and -1 for the cosmological constant. So the energy density dies off as a to the 4th power for radiation. It dies off as the 3rd power for matter, and it's a constant for the cosmological constant. So we also observe that the reason why radiation dies off faster than matter is that radiation also gets redshift in addition to matter getting diluted. So that's the explanation for the different powers of A for these two different components. So then we looked at different universes, and we noticed that, well, we looked at our universe, which has all these components, and we noted that at different epochs in the history of the universe, different components were dominant. So initially radiation was dominant. Radiation dies off as the 4th power, so it died off first. Then matter became dominant, and then matter died off, and then the cosmological constant is dominant today. And we noted that there were crossover regimes which described when one parameter was similar to the other parameter. And we noticed that radiation and matter were at equilibrium when the universe was a factor of 3,600 smaller than it is today. And we noticed that matter and cosmological constant were in equilibrium when the universe was 3/4 of its present size. So having done that, we then explored different kinds of universes we might have, and we're looking at the Friedman equation initially with energy density equal to 0. So all there is curvature. And the equation then looks like a dot squared is minus kappa c squared over r squared. And we noted that there were several solutions. So one solution was a dot was constant. So this is the empty, static, spatially flat universe, which is extremely boring. Then we noticed that the next solution was a dot is square root minus kappa over c over r. And this solution makes sense when kappa is negative. So we then have, for kappa is -1, A is C over R times T. So we're going to call this T over T0, and the universe is growing linearly in time. So I think that's where we left off. So we're going to explore this universe and then subsequently various other single component universes where we'll turn curvature off and turn on one component in the energy density, either radiation or matter or cosmological constant. Okay, so we've noted that in this universe, where epsilon is 0, the energy density in stuff is negligible. So we want to look at what this universe looks like. The Hubble constant, A dot over A, is just 1 over T0 over, it's just 1 over T0 for all T. And so this is the Hubble constant, and in particular, today, the Hubble constant is 1 over T0. So here, in this universe, the age of the universe is the inverse of the Hubble constant. That's only true for this universe and exponentially increasing universe. For other universes, there'll be some factors to go to front here, as we'll see. So this is just R over C. And we know the redshift is related to the scale factor. So light is emitted at time TE, and the ratio of the two is T0 over TE. So the redshift then lets us solve for the emitted time, which is the ratio T0 over 1 plus Z, which is H0 inverse over 1 plus Z. So given a measurement of the redshift, we can solve for the time of emission for radiation that we're now receiving. So then we had a couple of formulae that describe the proper distances to objects. And we want to measure the proper distances at time of emission and time of observation. So we know that dp of T0 is the integral 0 to R dr A of T0, which is 1, and that equals R. And we also know that if we take speed of light, multiply it by the integral from T emission to T observation, dt over A of T, we'll also get the scale factor, and this then is equal to the integral 0 to R dr, which is R. So the proper distance in the curvature-only universe, you can plug in what the scale factor is. This is TE to T0, dt over T0, which is C T0 log T0 over TE. So this is C over H0 log 1 plus C. So if we plot the logarithm, if Z is much, much less than 1, so that is close to the argument logarithm being 1, then this is linear. which is like Hubble's law. But if z is much, much bigger than 1, this grows logarithmically. So if we were in such a universe, we expect a different behavior for Hubble law, the relationship between distances and velocities, depending upon what the redshift was. So if you plot these things, plot h0 d over c versus the redshift, you'll find something which looks roughly linear to begin with, and then dies off. This would be dp t emission, and it's also roughly linear, and it goes like this, dp t0. So it's linear at the beginning, logarithmic later on. So let's see what happens to astrophysics, observational astronomy, in a universe with only current. So the first observation is that dp of t0, the proper distance as we measure it today, is much, much bigger than c of a0. In this limit, the redshift increases exponentially with the distance. So, is this weird? Possibly. It's weird in that we can see light sources with proper distance bigger than c over h0 when the age of the universe is only 1 over h0. So, given that the age of the universe is 1 over h0, the time it takes for light to travel when the age of the universe is c over h0. So somehow we're seeing light sources that are older than the age of the universe. That sounds sense. So the explanation for this is that at the time the light was emitted, the universe is smaller by a factor A of t over A of t observation, which is 1 over 1 plus c. So, the proper distance at the time of emission is c over h0 log 1 plus c over 1 plus c. And this has a maximum for z is e minus 1, which is 127. So at the maximum, dp of te maximum, this is 0.37 c over h0. So when light was emitted to us, the universe is much smaller, and the universe has since, the redshift has increased exponentially with distance. So it looks like objects in a very distant redshift have been emitted, light at a distance further away than we would expect. Okay? So this universe is a bit weird. But that's what the equations tell us, and this is evidence we're not living in such a universe. So it's good to exclude things. So a lot of observation is designed to test models. So the way a lot of modern cosmology works is we invent a model, and then we develop data, and we compare the prediction to our model to the data we see. if we see some obvious inconsistencies with the model and the data we see, we come up with our model. So this, the fact that we're able to test models like this is good evidence that our methodology is working. So remember, we're doing the scientific method without reproducibility, because we've only got one universe. So it's important we're able to test models like this. Okay, so that's the single universe with only curvature. And again, it's not our universe. So the fact that things are weird here is evidence that we've got to do better. So the conclusion we draw is that energy density is not negligible, and we worry about energy density, which leads us to further developments. So now we're going to look at a single component universe, which is spatially flat. This is a spatially flat universe, we kappa equals 0, and we just have an equation which looks like a dot squared over a squared is 8 pi Newton over 3 c squared epsilon. And this epsilon is going to depend upon what the stuff we have in the universe is. We also have then the fluid equation, epsilon dot plus 3 a dot over a, epsilon plus p is the same as, so p is w epsilon, so this is epsilon dot plus 3 a dot over a, epsilon plus w. And this guy equals 0. So we derived last time that we can look at this expression and rearrange terms to get epsilon dot over epsilon is minus 3 a dot over a, 1 plus w. And it's enabled us to say that epsilon w of a is epsilon w0, a to the minus 3 times 1 plus w. So now we plug this in to here. So a dot squared is 8 pi g Newton over 3 c squared, epsilon w0, a minus 1 plus 3w. So multiply 3 by a squared. This minus 3 times 1 plus w became minus 1 plus 3w. I did that. So let's try to solve this differential equation. And the simplest way of solving a differential equation is to guess the answer. So we'll make the ansatz. Then a of t. So what guess should we make? What's a natural guess to make here? The universe is very simple. What's a natural guess to make, given that the universe is very simple? Yeah?
Just all exponential?
Exponential would be a good guess, but it's not the right guess. It is the right guess for a particular case where w is minus 1. Otherwise, it's not the right guess. What's even simpler than exponential?
Another section?
What?
Another section?
No? What's the first thing you learn to differentiate that's non-trivial?
Constant expansion?
What?
Just constant expansion?
Well, constant's kind of trivial. Your derivative is 0, so I consider that kind of trivial. What's the first thing which is non-trivial which you learn to differentiate?
Linear expansion?
What?
Linear?
How?
Oh, it's not.
So let's just take this being proportional to t to the alpha. So this tells us then that A dot squared is going to equal t due to alpha minus 1. So, the left-hand side is A dot squared. The exponential on the left-hand side is 2 to the alpha minus 1. And the exponential on the right-hand side is A to the minus 1 plus 3w. So this equals minus alpha times 1 plus 3w. So we solve for alpha, and we get alpha is 2 over 3 times 1 plus w. So our guess doesn't really make sense when w is equal to minus 1, because the exponent then would be infinity. So except for w equals minus 1, this is the right guess to make, this is the right answer. So, A of t then, A's dimensionless, so we take t, we divide by some time scale t0, and the exponent we solve for is over 3 1 plus w. That's our answer. So, A dot then is alpha over t times A, which is, that tells us A dot over A is alpha over t, which is 2 over 3 plus w over t. So H0 is 2 over 3, 1 plus w, 1 over t0. So this tells us that the Hubble parameter we measure is proportional to the age of the universe. Proportionality constant is this guy here, proportional to the inverse of the age of the universe. So we've got A of t now. Let's plug it into the Friedmann equation. So we plug it into the Friedmann equation, we get alpha squared is 8 pi Newton over 3c squared, epsilon w0, 1 over t0 to the minus 3, 1 plus w alpha, which, when we plug stuff in, is 8 pi Newton over 3c squared, epsilon w0, t0 squared. Because alpha is 2 over 3, 1 plus w. This 1 plus w and this 3 cancel. We just go for the minus 2. So we solve for t0 now, and t0 is alpha 3c squared over 8 pi d Newton, epsilon w0 to 1/2, which is 1 over 1 plus w, 1 over 6 pi d Newton, epsilon w0 to 1/2. So we solve for the age of the universe in terms of the energy density today and the equation of state parameter w. So there's some algebraic calculations one has to do there. When your ability to do algebra is inversely proportional to your distance from a blackboard. So I'm not going to show you how to do the algebra. Okay, so we looked at a spatially flat universe with a single term inside. The single term has a equation state parameter W, and we measured various quantities, the Hubble parameter and the age of the universe in this scenario. So let's notice a few things. So the age of the universe is given. So we notice the Hubble time. Hubble time is H0 inverse, and we're comparing that to the actual age of the universe, which is given by this formula here, T0. So in a spatially flat universe, if W is bigger than -1/3, the universe is younger than the Hubble time. And similarly, W is less than -1/3, the universe is older at the Hubble time. So here, epsilon of A is epsilon W0, A to the -3, 1 plus W. And this tells us that epsilon of T is epsilon W0, T over T0, the -2, and this is regardless of what W is. The exponent here is always going to be -2. What else have we seen? We've seen that the critical value of epsilon is 3c squared over 8 pi g Newton, H0 squared, and T0 is 2 over 3, 1 plus W, 0 inverse. So we have then that epsilon of T is 3c squared, H0 squared, 8 pi g Newton, 2 over 3, 1 plus W, H0 inverse squared, T to the -2. So just plugging in the value of T0 here, and plugging in the value today. We have then that this is equal to 1 over 6 pi, 1 plus W squared, C squared over G Newton, T to the -2, and this is equal to 1 over 6 pi, 1 plus W squared, the Planck energy divided by Planck length cubed, T over T Planck to the -2. Okay, so this is the expression we have then. The energy density in terms of the fundamental parameters. Yeah? This is E critical 0, EC0. I'm sorry. Yeah.
It's important to use the Planck energy formula.
It's useful sometimes. Well, I wrote it this way just so that you express things in terms of fundamental parameters, just so that we have some natural scale. But you don't need to write this way. There's no extra content here beyond what we've seen previously. So, you know, it's useful sometimes. I wouldn't say it's important. Okay, so suppose you find yourself in a spatially flat single component universe. So you see a galaxy or some distant object at some redshift. What do you conclude? So we know that the redshift 1 plus z is a of t0 over a of te, and this is t0 over te to the 2 over 3 1 plus w. So we can solve for te. When we do that, we find te is t0 over 1 plus z, 3 times 1 plus w over 2, which is 2, 3, 1 plus w, h0 inverse, 1 over 1 plus z, 3, 1 plus w over 2. So, given a redshift, we can solve for the time the light was emitted, and we can then solve for the proper distance. Proper distance is c times the integral from te to t0 dt over a of t, and this is c t0, 3 times 1 plus w over 1 plus 3w, 1 minus te over t0, 1 plus 3w over 3, 1 plus w. So this formula is valid when w is not equal to minus 1, as we stated, but it's also valid when w is minus 1 minus 1/3, since we're dividing by this 1 plus 3w. Yeah?
Is that exponential to the t over t0 to the whole right?
Okay, so we can write this as well as c over h0 to 1 plus 3w, 1 minus 1 plus z, minus 1 plus 3w over 2. So, in this universe, the most distant object we can see is when light was emitted at te equals 0, the beginning. And it was detected today, t0 is now. And this corresponds to redshift infinity. So the most distant object we can see is at infinite redshift in this universe. Yeah. We don't. You can see redshift. We can only see redshift up to the CMB anyway, because before then, the universe wasn't transparent to light. If you have a device that detects your gravity waves. Gravity waves can be transparent, everything from the very beginning. So you can see gravity waves well beyond what you can see invisible radiation or in light. So if you're detecting primordial gravity waves, as a new window in the universe in very early times. We have not detected primordial gravity waves yet. We were looking. The horizon at time t0 is c integral 0 to t0 dt over a of t. And this is equal to c t0, 3 times 1 plus w, 1 plus 3w, which is c over h0, 2 over 1 plus 3w. So the horizon distance has a finite value. or W bigger than minus 1/3. So we're seeing, so the distance of the horizon is the furthest we can see light. So furthest we can see light will have infinite redshift as the universe, assuming we can see far back. So what this tells us is in the flat matter, so matter and radiation domination both fit the prescription that W is bigger than minus 1/3. Radiation W is 1/3, matter W is 0, so both numbers bigger than minus 1/3. So in a flat matter or radiation dominated universe, in such a place, we can only see a finite part of potentially infinite volume. So we call the part of the universe we can see the visible universe. So the universe in this setup being much bigger than we can see, we're just entitled to see a finite part of it because the speed of light is finite and the age of the universe is finite. So this is the part of the universe from which a light signal can be received within the age of the universe. So we can also say this is a part of the universe to which we're causally connected. Special relativity tells us that a light signal can't be received from a particular point in space-time. That event at that point in space-time can't affect anything we do. Okay? So for W less than or equal to minus 1/3, all of the universe is causally connected. So any point in space-time can potentially influence the decision we take today in such a universe. We can see infinitely far, whereas before we could only see finitely far. But very far away light is extremely redshift. It's very difficult to detect light which is super far away. So this is a particular universe with some equation state parameter, W. And also with set cap equal to 0. So now we're going to specialize particular values of W. First we'll specialize the matter, then we'll look at radiation, and then we'll look at the cosmological constant. Okay? And those will be our model universes. So W is equal to 0 now. So if we plug in the formulas we derived, T0 is 2/3 1 over H0. And the horizon distance today is 3c times T0, which is 2c over H0. So this is, we measured the Hubble parameter, and this is how far back we can see today. That's the distance to the horizon. So the rest of the universe, at distances beyond the horizon, is not causally connected to us. So events out there couldn't influence our decisions here, so we don't know what happened out there. Okay. The scale factor, AMT, behaves like T over T0 to the 2/3. The universe increases as a power law, and the power is T to the 2/3. The proper distance today is C integral dE T0 dt T over T0 2/3. So this is BC T0, 1 minus dE T0 1/3, which is 2c over H0, 1 minus 1 over square root and plus c. So all I've done is take the formula that I've written down previously, plugged in the value of W equals 0, and written the same stuff down again. Okay, so you know how to derive these. That's the proper distance as measured today. The proper distance when the light was emitted, we also have a formula for that. So dP dE is 2c raised to 0 plus c 1 minus whatever c. Okay, so this has a maximum. The max is at z is 5/4. And proper distance at the maximum is 8 over 27 c. Okay. So what we've seen is that in such a universe, we have a linear relationship. And the slope is 2/3. So that's the power. We've also seen that if you compare proper distances at TE and T0 as a function of redshift, the proper distance for the observation will go something like this, and the proper distance for the emission will go something like that. And the maximum corresponds to this value, z is 5/4. So that's a matter-only universe. Again, that's not the universe we live in, but if we were to live in such a universe, this is how things behave. And for a period in the history of the universe, This is how things in fact mostly behave, because this is mostly matter dominated. So that's matter. Now you can do the exact same thing for radiation and write down similar formula for various things. So let's do that. So we noticed that radiation came before matter. The universe was initially radiation dominated, and then it became matter dominated. So for radiation, W is 1/3. Things are moving relativistically. T0 is 1/2 H0. The horizon is at distance 2c T0, which is c over H0. The scale factor A of t is t over T0 to 1/2. The proper distance dp T0 is c integral dE T0 dt t over T0 to 1/2 is 2c T0, 1 minus dE T0 to 1/2, which is c over H0 c 1 plus c. And dP of TE is C over H0 1 plus C, 1 minus 1 over 1 plus C. This is C over H0, C over 1 plus C squared. And this achieves a maximum at z equals 1 with dP of TE is 1/4 C over 0. The universe again increases with slope here is 1/2, whereas before it was 2/3. And if you look at the behavior of the scale factor, you get a similar curve with that's these are dP T0 and dP of TE will end up looking like that. Okay, so that's the difference between radiation domination and matter domination. During radiation domination, the universe was increasing its scale factor at a smaller rate. The exponent of 1/2 instead of 2/3. So now we've studied two universes, one that's radiation dominated and one that's matter dominated. And we want to move on to the cosmological constant dominated universe. But let me say a few more words about radiation domination before we do that. So we're stepping backwards in time. We start off with matter domination, and then we go to radiation domination. And we noticed that radiation domination, there was an extra factor of the redshift, which accounted for how fast energy density died off. So the flat radiation dominated universe, energy density of radiation is a function of G. Energy density of radiation today T over T0 to the minus 2, which is 3 over 32 dp LP cubed T over TP to the minus 2, which is approximately 0.094 dp LP cubed T minus 2. So in the early universe, when the radiation was a strongly dominant feature, we know the relationship between temperature and scale factor. So temperature is going to be 45 over 32 pi squared for 1/4. Numbers currently don't matter very much. TP, T over TP to the minus 1/2. And this is using the black body distribution. So the Planck temperature is 1.4 times 10 to the 32 Kelvin. So this this expression here tells us that the mean energy for radiation at a time t is 2.70 K Boltzmann T of t, which if you plug numbers in, works out to 1.66 times the Planck energy T over Tp to the minus 1/2. So the number density at a time t is the energy density of the radiation divided by the mean energy at a time t, and this works out to 0.057 over Planck volume T over Tp to the minus 3/2. So the reason I express things this way is we take the limit where T goes to 0, then in this limit, the energy density of the radiation goes to infinity, the number density goes to infinity, and the mean energy, all function T, goes to infinity. So we notice that everything is infinite in the limit where T goes to 0 in a radiation-dominated universe. So how should we interpret all of these infinities? We're saying here basically that there's infinite energy density, and the infinite energy density is carried by an infinite number density of photons, which is each of which has an infinite mean energy. So this is the statement that we're making in this limit where T goes to 0. So the interpretation is that we shouldn't take any of this seriously. And the reason is that the energy densities were infinite, then the assumptions that went into general relativity, that things were smooth, would break down. So you shouldn't take infinity seriously. So we'll see that the universe went from radiation domination to inflation domination to radiation domination again to matter domination to random domination. So this happened roughly 9 billion years. This happened roughly when the universe was 34,000 years. This period of inflation took place between 10 to the minus 36 and 10 to the minus 33 seconds. Radiation domination is the stuff in between and before, and the Big Bang here is time 0. So what we're saying is that as we take radiation domination up to the Big Bang, everything is infinite, and we shouldn't take things seriously. So The reason is GR is a classical theory. And whatever is happening at early times, we need quantum gravity. And because I've been in this business for a while, I'm prejudiced to what I think quantum gravity is. So your guess is probably better than mine for what happened at the beginning. Okay. So far, we've discussed radiation domination and matter domination. Now we'll turn to cosmological constant domination. Let's take a short break. So we looked at radiation domination and matter domination. Now we'll turn to Lambda domination. For Lambda domination, W is -1. So A dot squared is 8 pi g Newton over 3c squared epsilon lambda A squared. So here, epsilon lambda is the same as epsilon lambda 0 since it's a constant. So we solve. So notice the equation here is A dot squared is equal to A squared. It tells us the solution is exponential. So A dot is H0 times A, where H0 is the square root of 8 pi to 3c squared epsilon lambda. So A is the exponent H0 minus P0. The universe in this case is exponentially expanding. So the proper distance dp 0. This is c times interval te t0 dt e to the h0 t0 minus t, which is c over h0 e h0 t0 minus te minus 1, which is c over h0 as a redshift c. So the proper distance is linear with a redshift. And proper distance at time of emission is c over h0 z over 1 plus c. As usual, in going for the proper distance at time t0, at time te, we divide by 1 plus c. Okay. So for object universes, besides the one which is lambda dominated, this relationship that's linear between the proper distance and the redshift is only true for small redshift. Here it's true for all redshift. Okay? So as z goes to infinity, dp of t0 goes to infinity, and dp of te goes to c over h0. So highly redshifted objects, so objects that are at large redshift, appear to be having an infinite proper distance, and the light which they emitted was emitted when the proper distance was c over h0. So that's the conclusion we have here. So once an object is at a distance further than c over h0, then its recessional velocity is bigger than the speed of light, because z is bigger than 1 at that point, and light can't reach the observer. Okay? We can only see back to this distance. And when we see back to this distance, it looks like the distance to that object is infinity, And anything further back, the light hasn't reached us yet. So we can only see a part of the universe with this phone. Okay. So in this universe, we've noticed that the scale factor increases exponentially.
With the emission proper distance, how is it possible that when z tends to infinity, that distance tends to z over h while the equation is...
So today, the universe expands exponentially. So today, it looks like the light source is infinitely far away. When the light was emitted, the light source had a proper distance of c over h0. The universe is continuing to expand, right? So as the universe is expanding, the object looks to be further and further away because of the expansion. Does that answer your question?
But isn't the value of h0 going to be different since you're saying when this light was emitted?
So h0 is a dot over a today. So if you look at the way a looks like, so a is equal to e to h0 t minus t0. So a dot is h0 e to h0 t minus t0. So a dot, which is h0 times a. So a dot over a is h0. It's just the fact which appears in the exponential. Okay. Did I answer your question, or answer your question completely different from what you asked?
No, I was confused as you said. Initially, this light was emitted when the distance was that.
Right, so the picture is that the universe is exponentially increasing. So it looks, this is a scale factor. It looks something like this. This is 1 at time t0, and it's huge today because the exponential expansion. So the light, so if you look at a picture of the universe, it's really tiny. It's much, much bigger a small time later because of the exponential expansion. So today, if you're looking at light that looks to be coming from infinity, when the light was emitted, the universe is much smaller. And the redshift at infinity today corresponds to a proper distance at time of emission to be c over h2. Okay? So, whereas if you look at the different power laws we had previously, the universe is expanding t over t0 to the half, or t over t0 to a third, or radiation of matter. This is a much slower rate of expansion than this exponential expansion. So, so as a result, the universe behaves very differently today than it did in the past. So initially, radiation domination, the universe was expanding at a rate t to the 1/2. Then we're matter domination, the universe expanding at a rate t to the 2/3. And now we're at this exponential growth. So the universe is getting bigger, faster, and faster, and faster. That's what happened. So this is what leads people to suspect that the end of our universe is a heat death. Only things which are gravitationally bound remain within the horizon. Everything else flies away exponentially. So as a result, the only things that exist will be the Virgo supercluster eventually. Everything else falls out of our horizon, if not gravitationally downward. And as a consequence, if we don't know if this happens, but if protons end up decaying, then all that's going to be left is a bath of radiation. And as the exponential continues, this bath of radiation becomes cooler and cooler and cooler. So we know the temperature is dropping, like 1 over the scale factor. So this means because the scale factor is increasing exponentially, the universe is getting colder and colder and colder exponentially. And that's just oblique and the authority. But it may be that protons don't decay. We don't know that whether they do or they don't. We've never seen a proton decay. If they do decay, they've got extremely long lifetimes, so we don't need to worry so much about all the protons suddenly decaying. If they're stable, that's good. It means that stuff stays stable for a very, very long time, maybe infinitely long. So there could be structure in the universe for a very long time. But the maximum complexity you can have is the Virgo supercluster because everything else flies away gravitationally. So this puts a maximum limit on how complicated life can be, for example. And one of my colleagues is very frustrated by this notion that it's maximum complexity of life. These are the things you think about when you're a physicist. How complicated can life ever get? So the proper distance, we had some plots to show how the proper distance behaves. So in this universe, dp versus redshift, the dp of t0 is linear with respect to redshift, while dp of te ends up achieving a maximum. Okay, so these are the single component universes that we've encountered. We've encountered a single component universe, which is just curvature. This universe is weird, and it's not the universe we inhabit because it's ruled out on physical grounds. So it's not the case. It's a conclusion, curvature only. Conclusion based on studying this is that energy density of matter, radiation, and these all are important. And we can't treat these as negligible quantities. Then we looked at radiation domination, matter domination, and cosmological constant domination individually. So next week we'll look at these in various combinations. We'll also look at all of them turned on at once. If we look at turning on two of these, we can solve for things analytically. If you turn everything on, you can't solve analytically, you're stuck with numerics. And we'll see what the numerics tell us about the history of the universe when we turn everything on. We know that these things had different times for which they're dominant. So to a very good approximation, radiation, matter, and lambda treated individually work as a description of the universe for very long periods of time. It's only when these things are competitive with each other that we consider the case where the universe behaves in a combination of matter and radiation, or matter and lambda, or various other possibilities. So we'll see that when you turn everything on, the universe gets very, very complicated. It might be that there was no Big Bang at all. There could be various other possibilities for the history of the universe when everything's on. The differential equation is much more complicated. It admits more interesting solutions. We think the solutions without a Big Bang are ruled out by data. So that's again a good thing, is that we have models. Models make predictions. We test the predictions against data, exclude certain models, and come up with models that are more realistic, more descriptive of our own universe. So that's the aim as we continue. But for now, this covers the single component universes. So we pause and ask if there are any questions. Yeah.
How did you get the C over H and Z, the second line to the top and the second board?
So when you look at proper distance at time of emission, this one.
Yeah, I don't know solution.
I integrated this. Integrating this from TE to T0. So the integral of the exponential is the exponential. There's a factor of H0 here, so divide by H0. that's this guy here. And then I'm rewriting this in terms of dimension. Other questions? Okay, so tomorrow we'll plan on doing exercises. We didn't have time to do exercises last week, so if you've got questions on the homework set for last week as well as this week, we'll discuss those tomorrow.